Hello, everyone. This is our Wednesday live stream. Thank you so much for joining us. My name is Matthew, and I am one of the course staff doing a lot of the behind-the-scenes stuff. Also is Alexander and Victoria, who is not with us today, but does a lot of the work on the Twitch channel. So without further ado, we'll get started. Chris, I will let you say hello, and then we'll get right into questions.
Okay, welcome everyone to another live session for the online classes, and I'm looking forward to your questions on anything in astronomy.
Excellent. Our very first question is from an email. Sandra Gibson emailed and asked, if you accept the simulation argument, how does that change the study of cosmology, especially in regards to the concept of time and the evolution of the universe? And in astrobiology, it seems a pretty clean answer to the Fermi paradox.
Yes, so the simulation argument, just to recapitulate, since people may not be familiar with it, it's a provocative argument made essentially by philosophers that given there's a likelihood that we're neither the first nor the most advanced intelligent civilization in the cosmos, and given that a projection of our capabilities to create simulated environments and virtual reality with greater and greater fidelity to the real world is increasing, it's not implausible that an advanced civilization would be able to create simulated creatures like us. In other words, we could be living inside a computer simulation created by some other entity. And unlike the movie in the Matrix, where there are glitches in the Matrix and you can tell at points that you live in a simulation, the programming capabilities and the technology involved would obviously be very good. So there would be no seams or glitches or ways for you to tell you lived in a simulation. And the hypothesis is that this is a not implausible scenario, and that it's very hard to disprove, of course. And it does indeed address one of the questions, one of the answers to the Fermi paradox, the where are they paradox, by answering in the manner that they do exist, and they were more advanced than us, and they created us. It's quite kind of a bizarre answer to the question. The question of how it changes cosmology is sort of the same as the answer to the question of how it changes anything, because if our entire existence and our perceived reality is actually a simulated construct of another intelligent entity, then cosmology itself also doesn't really have any true meaning, because what we perceive about the universe or measure through our telescopes or our experiments is also part of the simulation. There's a catch-22 about a lot of these arguments, because if everything's simulated, then anything you talk about or mention or consider is part of the simulation by definition. There's even a sort of physical version of the simulation hypothesis, which is, rather than a computer program, speculates that a superior intelligence, to trick us basically, might construct a physical version of the universe on limited scale. In other words, the Earth, the planet that we're on, is not a full planet, but it may be just a hollowed out construct, a physical construction of a superior intelligence. And the objects that we visited in space only have to be rendered at the level that we visited them, their surfaces essentially. The stars we haven't visited, so they are just lights in the sky. And the rest of the universe that we see through our telescopes, again, can be simulated such that that's what we would see with our telescopes, and not truly representing the vastness of space and time that we think it does. These are provocative arguments. They're controversial. Some people think they really don't have any credibility. They're obviously extreme arguments, solipsistic arguments, really. But it's interesting how hard it is to rebut the simulation hypothesis.
Excellent. Thank you very much. The next question is from one of our live participants. Roger Anderton says, new scientist this week points out relativists, or people who believe in Einstein's relativity, should abandon their sinking ship. Are you thinking of abandoning it? And the headline that he's talking about is this headline that says, "Bye-bye space-time. Is it time to free physics from Einstein's legacy?" And it just talks about the irreconcilability of the two.
Right. I haven't read New Scientist Online in this issue, so I don't know what the article's about. I'm aware of some of the tensions that go with relativity. Now, if we're talking about general relativity, the Einstein theory of gravity, there are indeed tensions associated with that theory because it's an incomplete theory of gravity. We know that. We've known that for quite a while because it doesn't accommodate quantum scale phenomena. And these conflicts become acute when you're talking about something like a black hole, where you have to consider quantum scale processes at the event horizon or even inside the black hole, and our theory simply doesn't let us do it. However, you have to be careful in these headlines of science magazines, even reputable ones like New Scientist, to throw the baby out, not throw the baby out with the bathwater. There's a lot of experimental verification of Einstein's basic theory of general relativity. It's made predictions that have been tested and have stood the test of time. The existence of black holes is a prediction out of general relativity. The existence of gravitational waves and gravitational lensing, two phenomena that are now well documented, part of the standard landscape of physics, were both predictions from general relativity. General relativity has been tested in the weak gravity regime many times in terms of time dilation, gravitational redshift, precession of the perihelion of Mercury, one of the original tests, and has passed these tests with flying colors. That's not to say that it's the final and ultimate theory, but I'm not really willing to go along with these sort of kind of polemic stances on relativity that really say that it's in a crisis and needs to be thrown away, because for simplicity's sake, you actually need something to replace it with before you throw it away. And I haven't seen, there are alternative gravity theories, definitely, and some are under active investigation, but they have not reached the maturity or explanatory power of general relativity yet.
All right, the next question is from Hernan Reyes, who sent an email and is on with us live. Suppose that funding was not an issue. Would it be possible, and would it make sense to set up a research station on Europa's surface? So I assume for living, people to live there and do explorations. Are there problems with that? Would it be worth it?
It would be a wonderful thing to do in some future where we really had a lot of money to explore in the solar system. It would be an exceptionally challenging place to have people for a number of reasons. So scientifically, would it be interesting? Absolutely. Having a research base there would give you the latitude to drill down through the ice crust and explore the European Ocean and potentially see if there was biology there. That's the biggest thing you could possibly do. It may be possible to do that robotically, but not with any of the missions that are currently planned. The reason why it'd be exceptionally challenging compared to anything else we're imagining, like going to Mars and having a base there, is that we're in the outer solar system, so whoever goes there will be essentially 1 billion miles from home, years from home, not just the 8 months or a year of Martian colonists. So essentially they have to commit almost to a lifetime there, the rest of their natural lives. It's an extreme environment, not just from distance from the sun, but Europa has no extensive magnetic field, so the cosmic ray and radiation environment is extremely harsh. Obviously, there's no atmosphere on Europa; it's an almost perfect vacuum, so you'd have to make a completely contained habitat. Unlike the Moon or Mars, where we actually do have rudimentary technologies, if you remember the book and the movie The Martian, for growing crops or hydroponic farming, Europa really provides nothing to help you. There's water there, of course, in a frozen form, but there's very little else that would help you survive and subsist there. So I think it's such a challenging environment that I really don't see us living out there for a very long time.
Excellent. Thank you very much. The next question is from one of our live viewers. World of Science would like to know, how are the brain and the universe related or connected to each other?
Well, in interesting ways. They don't seem very similar. The human brain is a small 1 or 2 pound organic nerve center and thought center inside one species on the Earth, and the universe is some vast construct of space and time containing hundreds of billions of galaxies and trillions and trillions of stars. They don't seem related. They're related, though, in two obvious ways. One is that the universe evolved such as to make brains possible, or to create the possibility of brains in their existence. That's an obvious statement, but the universe had to have certain properties to allow life to evolve and intelligence to develop. So that's one connection. And the other connection is that our brains, even localized within our bodies on one planet around one star in a small part of the Milky Way, are able to understand at some level and encompass the entire universe. So these small squishy items inside our skulls are able to contain within them the concept of the entire universe. Well, that's pretty interesting. So those are the two essentially trivial but important connections between brains and the universe. The deeper potential connection is whether or not the universe has particular properties that would allow or could allow brains to evolve, which means intelligent creatures to evolve, to observe the universe. Because it didn't have to be that way. The laws of physics could be different, the properties of the universe could be different, and the universe would be a sensible place in terms of causality or physics, but it might not be a place that includes biology or intelligent creatures. These ideas are called anthropic ideas that somehow relate the properties of the universe to the existence within the universe of intelligent sentient creatures. I'm not a great fan of anthropic arguments, but those are the type of arguments that seem to seek to make a more profound connection between brains and the universe.
Thank you very much. The next question is from Lawrence K., who's on with us live. Lawrence would like to know, is dark matter uniformly spread across the universe, or can there be clusters of dark matter forming separate dark structures? And can dark matter interact with itself?
So these are interesting questions. The distribution of dark matter is an interesting issue, and it's one that astronomers think about a lot and try to measure as well as they can. Dark matter is widely distributed through the universe. It exists on all different scales in the universe, not just on the scale of galaxies, where obviously there are halos of dark matter, which are concentrated, within which the visible parts of galaxies sit. And those dark halos essentially provide the binding energy to keep galaxies together, because they provide 70 or 80% of its mass for every galaxy. So dark matter is not smoothly distributed. It clusters on the scale of individual galaxies where it forms dark halos, but also on larger scales, on the scale of clusters or superclusters. So basically every scale in the universe that has bound structures or collapsed structures of stars and galaxies is indicating dark matter that's clustering on those scales. And typically dark matter has less degree of clustering. It's less clumped, if you like, or less centrally concentrated than the visible matter. Because the visible matter in astrophysics has ways of collapsing and radiating away energy which accelerate the collapse, and for example the formation of gas into stars, that process, which leads to a small concentrated set of stars within a dark matter halo. Dark matter can only interact by gravity, not by any other forces, so it just gradually increases its concentration according to the laws of gravity. So denser regions continue to get denser slowly over cosmic time. And that's what we see through the universe. But with weak lensing and other methods, we can certainly map out dark matter across the entire visible universe, not just in specific galaxies or their halos. And indeed, dark matter is distributed through the universe, not completely smoothly, but without any great variations. The last part of the question of whether dark matter interacts with itself is an interesting one. And at some level, yes, it does, because the dark matter particle, we're assuming a fundamental particle here, has mass, and so it exerts gravity. And so yes, dark matter is self-gravitating, if you like. It exerts gravity on itself when it's in some region of space. It's not clear whether dark matter has any other type of interaction with itself, because that would mean knowing what the physical fundamental form of dark matter is, and at this point we simply don't know that.
The next question is one that I'm not surprised has come up. There's been some recent sad news in the astronomy world, and Hemi-Visible, Dennis Buller, and Jordan Stone would all like to know if you can talk a little bit about the collapse of the Arecibo telescope, the Arecibo radio telescope, and what are the consequences for astronomy and both current science projects and the future of astronomy?
Sure, I will, and I'm personally saddened. This is it means something to me. I first went to Arecibo to use it as a radio telescope 30 years ago, and I went, I think, 6 times over a period of about a decade. Haven't been for quite a while. And so it's a personal loss because it's an incredible, iconic facility in astronomy. I guess there's sort of 2 things to talk about. I mean, one is the destruction, the loss of the telescope, and then the other is perhaps the scientific legacy. So let me treat those as sort of 2 separate questions. The loss of the telescope is a sad day in astronomy because it was one of the biggest facilities in astronomy. As many people know, it was no longer the largest radio telescope or telescope of any kind on the Earth because the Chinese built a 500-meter radio telescope on a similar principle, and that is the largest radio telescope and has been for a few years. But Arecibo got there first. It was close to 60 years old, and its productive lifetime was much longer than many telescopes, in fact. So it did amazing work. I would say as a physical structure, Arecibo embodied the can-do engineering mentality of the 1950s, when a lot of incredible civil engineering and construction projects were made. When you go to the site of Arecibo and you see in this karst country these limestone etched undulations covered with rainforest, if you could have just imagined taking an aerial photograph and seeing one that was 300 meters across and saying, we can put a radio telescope there, held up by 3 towers, each the size of the Washington Monument, with close to 1,000 tons of hardware detecting the radio waves suspended on wires at the center of the dish, people would have laughed. They would have said, that's an outrageous thing to do. Well, that's what they did. So they built this during a time of massive and impressive engineering projects, a sort of can-do style of engineering that maybe has gone away a bit since. So it did have a long productive lifetime. It's in a very harsh environment. Puerto Rico obviously has an enormous amount of rain. The rainforest is an enemy to metals in general and to all sorts of constructions in general. Wear and tear of use for decades, hurricanes, and just generally extreme weather, even outside of a hurricane, high winds, for example. It's taken a lot of abuse over the years, and so it maybe was never going to last forever. Now, there's some recriminations going around because it really does seem like, since it moved out of the hands primarily of the National Science Foundation and Cornell University, which was the managing organization for the first decades, it's changed hands a couple of times. It's had funding crises, and it's essentially been starved of funds as astronomers put their money into newer, sexier projects. And so many people close to the project, and I'm sympathetic with this view, think that it was essentially neglected, and so a lot of the wear and tear and deferred maintenance finally caught up with it when these guy wires, these incredibly impressive cables that hold this structure together and suspend the feed above the dish, eventually started giving way. And it was due to be demolished because of the first 2 accidents that had happened, but in fact the entire central construction crashed down onto the dish, 900 tons of it, an incredible thought, dropping hundreds of feet onto the metal mesh. Luckily, really, no one hurt or killed, no engineers or technicians were around, but that's the end of the telescope. It has to be dismantled now. So it's a sad end to a telescope that had a long, productive lifetime, and I don't think it's going to be replaced in that sense. To answer the other question that goes with this, with the loss of a telescope, you look at the legacy of the telescope. When Hubble Space Telescope shutter goes quiet for the last time, people will do retrospectives of what will be 40 years worth of Hubble data, an incredible legacy. Well, Arecibo has a legacy of nearly 60 years of radio astronomy, and it's a remarkable legacy. It did foundational work on pulsars especially. It really did amazing work on pulsars. Also, a lot of what Arecibo did was ionospheric research, was working on the ionosphere of the Earth, on its transmission capabilities, its ability to reflect radio waves and so on, and just simply its chemical properties. Arecibo did amazing work on galaxies. That's what I used it for. I used it to measure the gas content in neutral hydrogen of dwarf galaxies, low surface brightness galaxies, and so on. And it's such a powerful facility that I was able to measure dozens of galaxies a night, hundreds in an observing run, enormous amounts of data that were impossible to obtain otherwise. So it's contributed to all sorts of fields of astronomy, and its scientific productivity is really quite extraordinary for any facility. It is a specialized community, though, because radio astronomy is a niche, if you like. It's a smaller field than optical astronomy, and so many astronomers never got the pleasure of using the facility, and I'm glad that I was one of the ones who did.
Excellent, thank you very much. Mary Donnell sent an email, and she's almost finished the original Coursera course on the astronomy course, and would like to know more about topics in astronomy, particularly cosmology. And other people have asked this before, and so it might be a good time to refresh us again. Do you have any book recommendations that would cover topics in astronomy and cosmology that are sort of at an amateur introductory level?
Mm-hmm. Sure, there are a lot of books. Actually, there are almost too many, because there are dozens of good astronomy popular level books, some with a little more technical detail than others, every year. And so it actually gets hard for me to just pick out a couple without notes to refer to. But yes, there are books on cosmology, and there are books on extragalactic astronomy. There were a spate of books written on the discovery of gravitational waves. I would say one that I would recommend in that area is Black Hole Blues by Janna Levin, because it's a more personal account. She was prescient actually, because she interviewed the LIGO scientists, the theorists, and the observers, and the experimentalists in the years before LIGO went online, and then she kept up with that project and published her book just around the time gravitational waves were discovered, and then the Nobel Prize was awarded within a few years after that. So Black Hole Blues is a book I definitely strongly recommend. It gives a flavor of astronomy and also the people involved in the subject. There are a number of good books on exoplanets, of course. That's a very hot topic. Adam Frank, I don't remember his exact title, but if you look for Adam Frank, he wrote a very good book on exoplanets and the search for life in the universe, just 2 years old now. So that's another area. In cosmology, it's a little harder to say, because there have been a series of books. Martin Rees has written a series of books on cosmology over the years, and I can't remember if his most recent book was on it. I have a feeling his most recent book was on the threats facing humanity in the future. So that's his most recent book. But if you go back one book before that, he's written beautifully on cosmology, several books. So anything that Martin Rees has written, I highly recommend. He's the Astronomer Royal of England. He's the president of the Royal Society. He holds Newton's chair at Cambridge. You can't get higher in the tippy top of the mountain of astronomy in the UK than Martin Rees. And he's also a Lord. He's the only scientist, not just the only astronomer, but the only scientist in the UK who's in the House of Lords, a high honor. So those are a few examples, but there are many good books on astronomy every year. It's well served. And I've written a couple myself.
Exactly. I was going to mention that we're doing readings of your books. Victoria's doing readings of Einstein's Monsters on Mondays. So you should check out our Twitch channel, which is Teach Astronomy, and you can check out some stuff there. And then the Adam Frank book was called Light of the Stars, Alien Worlds and the Fate of the Earth.
Nice book, Adam Frank. He's a stablemate. I've had 4 books with Norton, a publisher, and he's one of the He's one of the authors in Norton. So is Neil Tyson, actually. And since I will get to toot my horn, since cosmology was the question, I have written a book called How It Began and a book called How It Ends. They're essentially the bookends of the universe, at the beginning and the end, and they're pretty decent.
The next question is from Jim McLeod. Welcome back, Jim. He joins us frequently. Who asks, Dr. Impey, had you been on the selection committee for for the data to be included on Voyager's golden record, what picture, what song, and what sound would you have wanted to add to the disk?
That's an interesting question. So the Voyager record that many people have heard of, there are two messages in a bottle that we've sent outside the solar system on space probes launched in the 1970s that have traveled past the planets and now have formally left the solar system. There were the Pioneer spacecraft, which had a plaque attached to its leg, giving the position of the solar system and showing silhouettes of two humans and so on, and various other pieces of information. Slightly more ambitious, and a few years later, was the Voyager Record, designed to be attached to the Voyager spacecraft, which has also left the solar system now and probably is about 10 billion kilometers away at this point. This record is an old-style record. It's actually not 33 1/3; it's a half of that speed. So it's a lower playing record than even an LP. That was to get more information on it when they coded it. It's anodized gold. It's attached to the body of the spacecraft it's covered with a plaque. Covered with a metallic cover, which has on the inside instructions of how to get information off the record, because an alien intelligence would have to figure out that this is analog information, and they have to extract it from the variations in the grooves on the record. And there was a committee, famously involving Carl Sagan, Frank Drake, Timothy Ferris, I can't remember all the names of the people involved, Don Goldsmith, I think, was another one, that decided what would go on this record, Speaking for Humanity. Of course, there are musical selections. The classical ones are uncontroversial, of course. They're just the greatest hits of classical music. The popular songs were frozen in time, of course, in the 1970s, and that's before rap, before a lot of rock, before whole genres of music. And I don't know that these mostly old white men would have picked those genres anyway. So the musical selections have been critiqued heavily over the years. Well, you can't win that competition. Everyone will have their own ideas. There were a set of images digitized and included, and there was also the sounds of the Earth. There were greetings from the Secretary General of the United Nations at that time, who I think was U Thant, a Thai person, and greetings in, I think, 110 world languages. Also digitized on the record. So I wouldn't mess with that. Greetings of the world's languages is a nice thing to do. I think the images were a reasonable selection of human activities, what humans get up to, and the topography and beautiful landscapes of the Earth. Yeah, the music is probably the most controversial part. And so I'm not quite sure. That's almost too hard a question for me to answer on the fly, what music I would select that wasn't on it. I think there was some jazz that wasn't represented that I would represent because it was iconic. I think there's some more modern music, of course, modern popular music and rock music that I would want to put on. And I think even some folk music from different parts of the world that I would want to include it to give it more of a world flavor than the music that was on the record. But it's worth looking at. There was a book that since went out of print which bundled a CD of the Voyager record and a book explaining how the choices were made. I have it on my shelf. It's very unfortunate that it went out of print because it's a fascinating project. I think there are now web pages where you can learn about what's on it.
Yeah, as a matter of fact, I believe there is a JPL site that I will post in the chat that has information, that has everything that's on the record. So you can go check that out. The next question is from Dylan Wardlow, who's on with us live. Can you talk about what is the value of citizen scientists or volunteer scientists in the modern landscape of space sciences?
Yeah, citizen science is an important phenomenon of the sort of modern era of astronomy, the last 20 or 30 years. And the goal is phrased very simply. I mean, there's outreach. There are projects which are designed to share the wealth of scientific and astronomy information with the public and transmit it. Citizen science is a little different. It's the idea of getting members of the public, not trained professional scientists, to work with real astronomy research data sets and do meaningful tasks. Now, some citizen science sort of devolves a little bit to busy work, and you wouldn't necessarily consider it very meaningful, even if it's engrossing. But the best citizen science actually has citizen scientists doing, under instruction and having a little training data set before they start, something meaningful. And the archetype, of course, is Galaxy Zoo. That was the mother of all citizen science projects in astronomy, which had people classifying galaxies. And it turns out that AI and machine learning methods are pretty good at classifying galaxies, but they're not perfect. They miss some things. They can decide an elliptical against a spiral, but they're not so good at spotting a supernova that may be going off in a spiral arm somewhere, or a subtle asymmetry of a galaxy, and so on. So citizen scientists have been very useful in classifying galaxies, and they do it as well in certain controlled experiments as professional astronomers doing it. So citizen scientists are making valuable contributions. And now the wealth of astronomy projects has expanded into pulsar, working with pulsars, working with data from the Stardust project that looking for tiny microscopic extragalactic extrasolar dust particles in the aerogel on the Stardust mission. These are just a few examples. Working with the light curves from the Kepler project to try and pick out exoplanets that the algorithms and computer software didn't pick out, and people have had success in doing that. And I think in totality, I saw this number recently, citizen scientists associated with what is now called the Zooniverse project, which is the umbrella for citizen science astronomy, have contributed to and been co-authors on 300 refereed publications. Well, that's a really impressive statistic. They've also made there are also hundreds of thousands of citizen scientists that have made literally tens of millions of classifications or designations for objects in astronomical data. So this is not a small-scale activity. It's a really quite impressive, big activity. And there are many ways to get involved, and the easiest way, of course, is to go to the Zooniverse website. And I think at the moment they, of course, have citizen science in other areas, archaeology, anthropology, linguistics, and so on. There's many. There are about 17 astronomy projects that are currently active.
Thank you very much. The next question is from P.T. Cruiser, who would like to know, is there any correlation between the plane of the Milky Way and the plane of the planetary systems in our galaxy?
That's an interesting question, and you might imagine that there could be. But in practice, it turns out that there isn't. There's an angle of several tens of degrees between the plane of our solar system and the plane of the Milky Way galaxy. And you can tell that's true because if you go to a dark place where you can see the Milky Way, and then you look for the planets that are visible in the night sky, or the moon, which is also on the ecliptic, you can clearly see the difference between the plane of the solar system, which is where the moon and the planets will move, and the plane of the Milky Way, which you can see on a dark sky. And in general, that's going to be the case. Planetary systems form from gas clouds that are very, very small scale compared to the size of a galaxy. And they form under their own gravity. So essentially, a gas cloud that collapses to form a star and planets is sort of oblivious to the larger gravity field of the galaxy that contains it. And that's the simplest way of saying that the formation axis or plane of a solar system is really independent of the plane of the galaxy and has no relation to it. So we would expect planetary systems in their orientation of their plane to be randomly oriented relative to the Milky Way.
Excellent. The next question is from Ayush, who would like to know if expansion of the universe was reversed and the universe started contracting, would it become some kind of black hole or singularity after it all collapsed in on itself?
And the short answer is yes, because if you, we don't think the universe has sufficient mass, and because of dark energy, it's expanding too fast to ever recollapse. But if you did imagine somehow a reversal of time taking place from the current situation, so the universe just started getting smaller and the distance between galaxies all started shrinking, then eventually the temperature of the universe would go up. At some point, the density of the universe as it collapsed would be such that the integrity of individual galaxies would be lost, so the galaxies would sort of be ripped apart by gravitational and tidal forces, and the universe would turn back into a sort of particle soup, which is how it began in the Big Bang. And logically, if you follow that progression, the temperature continues to increase, the density increases, the universe at this point is completely smooth, no structure, no stars, no galaxies, no people for sure, and it projects towards a singularity. And that's because the self-gravity of the universe with this much mass in a small region of space is such that nothing can stop it from contracting to an infinite point of mass, which is a singularity. And that, of course, is the problem with the Big Bang going in the other direction, that we infer a singularity of infinite cusp of density at the Big Bang, which can't really be physically understood.
The next question is from Gaurav Agarwal, who would like to know, can we synthesize DNA using constituents from space in space itself?
No. At the moment, the chemical ingredients that we find in space do encompass a fairly wide range of molecules. I think the radio astronomers and infrared astronomers are the ones who typically measure molecules in space, because remember, deep space is actually mostly very cold. The regions where stars form are only 10, maybe 50 or 100 Kelvin, and the deepest regions of space are just 10 or 20 Kelvin. So these molecules betray their presence by rotation and vibration states, which are low energy and tend to have emission in radio, millimeter, or infrared regions. So with these kind of data, radio astronomers have detected, I think the number is something like over 100 different molecules in interstellar space in star-forming regions. It's quite impressive. But the largest, and it includes an amazing range of molecules, for some very interesting ones, ethyl alcohol, for example. But the largest of these molecules, I think, is only 15 or 16 atoms, maybe 17 now. And 1 or 2 amino acids have been found. The simplest amino acids, glycine, for example, I think it's 10 or 11 atoms, I can't remember, but it's a small number. And so these are the largest molecules that we can find in space. So the natural conditions of space do not seem to facilitate the formation of more complex molecules than, say, the simplest amino acids. So in terms of making even fragments of DNA or RNA, say, space doesn't really come close. We think that these complex molecules cannot form in the near vacuum of space, but they actually have to form in a liquid environment, such as the early Earth, where molecules can be concentrated and run into each other and build in complexity in an interesting way. And we don't think that can happen in deep space.
The next question is from John England, who's on with us live. If antimatter is the opposite to matter, does it experience the arrow of time in the opposite direction?
That's an interesting question. No, we don't think so, because the universe does contain antimatter, very little actually, but it can be created with equal facility to matter from pure energy. And the existence of dark matter in the universe, antimatter in the universe, doesn't connote the reversal of time necessarily, because antimatter just participates in particle interactions the way normal matter does. However, it is worth pointing out that in physics there are symmetries of time and quantum properties such that if you take an interaction between particles that moves in one direction in time, we see A and B turn into B, C, and D, for example, in terms of particles, then if you invert the sense of the matter in quantum properties so that these are antiparticles, then we can see the antimatter version of that interaction proceed in the opposite direction in time. So that's one way in which the time arrow can be reversed, because you can simultaneously reverse the time arrow and the quantum property to be antimatter rather than normal matter.
Excellent. The next question is from Volodymyr Usov, who is on with us live. What current missions do you consider most important for the progress of astrobiology? And what future missions do you think are important that are either being planned or being announced?
Right. Well, since the demise the Kepler Earths, or the sunlight, sun setting, if you like, of the Kepler mission. The mission, Kepler has a successor, and that's really annoying because the name of it is just flipped out of my head, which is designed to look for Earth-like planets and exoplanets in the nearby universe. Kepler was looking in one particular constellation, one region of sky, a small area of sky, so it was finding exoplanets that are quite far away. Its successor, launched also by NASA 2 years ago, is designed to look more across the sky for much more nearby exoplanets, and those are going to be much better for characterizing with ground-based telescopes. So that's an important mission. The ones that
You're
are
probably thinking of TESS.
TESS, yes. Sorry, zoned out on TESS. So that is the mission. Transiting Extrasolar Survey is probably some version of that acronym. There are another set of missions, and they're not fully funded or even fully nailed down, which designed to go beyond the detection or the bagging of exoplanets that are Earth-like and deciding if they're habitable or not, to truly characterizing those exoplanets. Euclid is a European mission that's relevant in exoplanet research, and that's an important one. But there's another set of missions that are pretty much 10 years away that are designed to characterize exo-Earths, and these are the exciting ones that people are hoping for. Unfortunately, 10 years in space astronomy is a long time, and budgets are not usually nailed down until 5 or 6 years before, so none of these missions is certain. Astrobiology is a very successful subject scientifically and with the general public, but it has not fared incredibly well in the competition for space missions, either in Europe or the United States. Astrobiologists are a little disappointed by that.
The next question is from Ruben, who is on with us live, who would like to know if you can explain why you think that we must know about astronomy and motivate new people, new generations of students to learn and to know astronomy. What's the point of it, but also what does the future hold for astronomy?
That's a good question. Astronomy is a small field compared to physics or chemistry or biology, so it's important to know what its status is and what its future is. The world could only hold so many astronomers because astronomers, they're not contributing very directly to the national good. They're not saving lives. They're not doing some other things that can definitely be considered more essential to society. But the search for knowledge and the search for understanding our place in the universe has value, and society values it, and not just rich countries, but even some more modest countries think it worthwhile to have astronomy. It tends to live mostly in universities, so the future of astronomy is a little bit tied to the health of the universities, since many, maybe the majority of astronomers, like myself, are employed by universities. The rest are employed at government agencies and various private foundations and private research organizations. So the world can't support that many astronomers. In terms of the future, I think the astronomy is stable. It's fairly buoyant because the successes and the research and the discoveries come in pretty much weekly. You can see the headlines pretty much every week in newspapers. So it's a very successful subject. It's not a dead end or a stagnant pool of water by any means. But I would suggest that in the next 10 or 20 years, that really doesn't amount to much more than very modest growth of astronomy worldwide. Now, there will be, relatively speaking, more growth in countries perhaps that are up and coming that haven't traditionally had a lot of astronomy. The poorest countries, I don't think, can really afford to do astronomy. It's not their priority. But there's a middle tier of countries, the newly industrialized countries, as they're called, that are actually developing physics and astronomy and all their sciences, and so we see increasing growth in those areas. A couple of obvious examples are Chile, which has, of course, is home to an incredible array of telescopes and is breeding their own large new cadre of astronomers, and not far away, Brazil, which is another increasingly wealthy country where science is important and where astronomy is becoming more important.
All right, the next question is from Janak Shrestha. Sorry if I pronounced your name incorrectly. I will work on doing better. Would like to know, why can't gravity squeeze the Earth as it can squeeze a huge star into a small dot?
It could, if there were a situation that could allow for that. The Earth, formed by gravity from interstellar dust, from tiny dust particles and gas that were gradually compressed over time into the solid object that the Earth is. For the Earth to be compressed further, it would have to be subject to forces that exceeded the tensile strength of rocks. And that's possible, but astrophysically it's hard to tell how that could happen. Essentially, the only way the Earth could be squeezed naturally to a denser state than it is if the Earth, and then presumably the whole solar system, became part of a much larger gas cloud, and that gas cloud then collapsed by gravity, and the Earth was then crushed along with the interior of that gas cloud. That's a scenario, at least, a hypothetical scenario, whereby the Earth could be crushed beyond the point it is now, which is rocks. Now, how much more could the Earth be compressed? Well, it could clearly be compressed more than the density of rock, because rock is mostly empty space. You get to a neutron star, you're talking about the density of neutron material, which is trillions of times denser than rock. And so with sufficient gravity, you could crush the Earth to the size of a neutron star. And if you would somehow manage a situation where the Earth squashed down to the size of a golf ball, the Earth would fit the formal definition of a black hole. And that's possible in theory and hypothetically. It's just impossible to imagine any real scenario in the universe where that would happen.
Excellent. The next question is from Red Unleasher, who would like to know, if a star were to pass by us, I'm assuming they mean through the solar system, but possibly nearby, what would be the consequences for us?
Yes, a close passage of a star would be a very interesting scenario, and probably not a good one for the Earth. We do know the position of the Earth, or rather the Sun, in the solar neighborhood, and so we know the nearest stars, and we know their motions, their space motions, so we can tell which stars, if any, are going to come close to us. And astronomers have written papers where they play forward hundreds of thousands or millions of years and show which of the nearest stars might get close to us and how close. And in the next 10 million years or so, as far as these calculations are reliable, there's no very close passage of a star to the solar system. But if a star did come within the solar system, just say a star passed within the orbit of Neptune and Uranus, it didn't have to come right near the Earth. Remember, Uranus and Neptune are dozens of times further away from the Sun than the Earth is. So imagine a star came that close. That would be catastrophic, not because of the radiation from that star, but really because of the gravity from that star. A star passing that close within the solar system, moving fast, would disrupt the orbits of the planets. If it disrupted the orbit of Jupiter, that could have a knock-on effect which would alter or destabilize the orbits of the terrestrial planets like the Earth, and possibly throw the Earth out of a normal near-circular orbit, even ejecting the Earth from the solar system. It'll take a while for that to play out, but that's certainly a possible outcome. Another outcome is that when a star got that close to the solar system, it would have passed through the Oort cloud of comets, which is a roughly trillion mostly dead cold comets that live mostly in the outer part of the solar system, well beyond the planets, that pass on highly elliptical orbits into the solar system. If the Oort cloud were perturbed or jostled or altered dramatically by the passage of a nearby star, that could trigger an incoming wave of comets the like of which we've never seen, or maybe has been seen in ancient history. And those comets would create a lot of impacts and devastation, a spike of impacts on the Earth, including impacts of 5, 10, 20 kilometer size objects that would be really quite catastrophic. So a star passing through the solar system, even if it wasn't a direct hit, that would be a pretty bad thing for the Earth and life on Earth.
And so Josh Kilburn had a kind of a related question. I think you pretty much covered it. I'll go ahead and just address it here, and if you think that there isn't much else to add, then we can move on. But Josh had just asked, have we discovered all the stars in our local neighborhood, and could there be any sun-like stars within 5 to 10 light years that we just haven't found yet?
The question of whether we found all the stars in the solar neighborhood is still a relevant one. There's no way a sun-like star could have been missing, that we couldn't have seen it, because a sun-like star is a bright object, and there's nowhere for it to hide within 10, 15, 20 light years. However, if we're talking about brown dwarfs, the lowest mass stars, or even substellar objects, black dwarfs, compact objects, maybe like a naked neutron star, it starts to become possible to have those objects nearby, and we might not have seen them yet. So people have pretty much tried to search for all the way down to the faintest red dwarf stars. And at the faintest edge of fusion limit, and at about 20 or 30 light years away, these stars are actually getting pretty faint, and so it's not necessarily the case that we found all of them. But that's really the only gap in our knowledge. For sun-like stars, we know where all of them are, out probably to over 100 light years.
Excellent. The next question is from RS Mu, who's on with us live. Voyager, the Voyager spacecraft, is still trying to figure out if it has left the solar system. Where is the boundary of our solar system?
And that's a question that we haven't known the answer to until recently. It was theoretical. So what astronomers have speculated for decades is that as you get past the solar system, there's something called the heliopause, and that is essentially a boundary layer between the sun's radiation and solar wind and high-energy particles that come off the sun, and the interstellar medium, the ambient medium between stars, which is not a complete vacuum. It's a density of about 5 to 10 particles, which is hydrogen atoms per cubic centimeter. And so the heliopause, Pioneer has passed through the heliopause, and so we've actually detected that transition layer, and it didn't occur where or in exactly the way that was anticipated by theory, but it definitely occurred. So as far as we know, we have spacecraft that have passed truly beyond the realm of the sun, or the reach of the sun and its radiation, into the true interstellar medium, and are measuring that for the first time, which is very, very exciting.
The next question is from Fadi Anwar, and the question, I'll kind of expand on it a little bit, is they would like to know what should somebody ask that you don't think anybody has asked you before. But to kind of expand on that, I think we could say, what's a subject that you think is really important and interesting that doesn't get kind of addressed in public forums or in questions as often as it could, or maybe you think it should?
These Q&A sessions are fun for me because they cover so much subject matter. So I really think you are all imaginative enough and have enough interest that I haven't seen any great holes in the questions I've been asked. I said the kind of questions I don't tend to get in these situations, which I like, and I've made a study of it, so I do know many of the answers, are about sort of the history of astronomy, which has a very long history. The major figures of astronomy, what they did, the early history of astronomy, the prehistory of astronomy, astronomy as it started when we were not in civilizations, or about more the philosophy of the subject, which is to say the method of science and the philosophy of science and how it plays into these big questions that people ask about the universe. So those are topics we don't tend to get as much about. I think within the realm of normal astronomy topics, cosmology is obviously popular. Astrobiology is something that I think is ascendant, and so I'm always happy with more questions about astrobiology because there's a lot going on that, which that of course includes the history of life on Earth as well as the prospects for life beyond Earth. But really, otherwise, the ground covered by the questions in this series of Q&As has been gratifyingly broad.
Excellent. The next question is from one of our live participants. Janeth Lopez would like to know, or Janeth Lopez would like to know, what are the possibilities of the existence of a wormhole?
It's a hypothetical construct of gravity theory, which is to say it's possible in principle and technical articles are written on this every year or so. And a nice non-technical treatment is a book by Kip Thorne about black holes and white holes some years ago, but it's still current because the theory hasn't really changed that much. So Kip Thorne in that book acknowledges that wormholes, which is to say a connection between disparate parts of the universe through a fissure, if you like, or a connecting tunnel between different parts of space-time, is possible in principle. Space-time can be curved. That's general relativity in its most basic form saying that. And it can have complex curvature or topology. And so it's entirely possible within general relativity to have highly convoluted space-times, including space-times that are interconnected in the way that would match what people think of as a wormhole. So it's absolutely possible in theory. In practice, not nearly so clear, because the universe seems to be rather simple. Space-time that we've measured so far seems to be almost perfectly flat. Certainly the larger universe around us is flat space-time in 3 dimensions. And finding space curvature is only possible in very extreme and localized situations of high-density objects, and not anywhere else. And in none of those situations is there sign that the density of an object that's collapsed space-time is connected it to a different part of the universe. So there's no evidence for wormholes at the moment.
The next question is from, I think a couple of people have asked this, but specifically Aryan has posted this. And this is about, they say space expands, but we know that planets don't and stars don't. So what is it that's expanding? And if you consider that the space between these stars and planets is increasing, then what about things at different scales, essentially?
So in its essence, when you're talking about expanding space-time, you have to drop back to the general relativity description, which is a mathematical description of physics. And the mathematics of general relativity describes space-time as what we would call a manifold. That's a mathematical term for multidimensional spaces. Hypothetical, abstract spaces. In this case, it's the 3 dimensions of space and the connected one of time. And so general relativity's description of space-time is a mathematical description of a medium, which doesn't have to have any matter in it, where the medium itself is expanding, not into anything and not with reference to anything else, but just within its own definition, it's expanding. And as it expands, objects within the space-time are carried apart. And that's where the analogy of the balloon that's often used for an expanding universe is actually valid. If you imagine a balloon where little beads are glued to the surface of the balloon, those are the galaxies, because the galaxies don't get any bigger as space expands, then blowing the balloon up moves all the galaxies, the beads, away from each other, just like Hubble expansion. And it's actually the medium of the rubber of the balloon that's expanding and carrying those objects apart from each other. And it's a 3-dimensional version of that, a 3-dimensional analogy of that, where the galaxies are being carried apart from each other by the expansion of the medium itself, the space itself, which has a purely mathematical description.
Excellent. It is 2 o'clock, so I think we will take this as our last question. And it's from a user called 800 Millimeter Telescope Project, who asks, if gravitational waves travel at the speed of light, how can lasers as a measurement tool be used to measure them?
Well, so gravitational waves are ripples in space-time. That's a colloquial way of putting something that's really defined in terms of the theory of general relativity, but let's think of them as ripples in space-time that propagate at the speed of light. So the means of detecting those ripples is to have a cavity, a vacuum on Earth, and that is done at the LIGO facility, and it's 5 kilometers long, and we bounce light backwards and forwards in that cavity. The idea of making a vacuum of the cavity is so that the light isn't interacting with air molecules. And at the apex of a triangle, where there's a 90-degree apart path of 5-kilometer arms and light bouncing backwards and forwards in these two arms. At the apex, at the joining of these two arms, you measure the movement or the displacement or the change in the shape and size of what's called a test mass, and that's just a large metallic object, very pure metal, that's suspended from the geothermal noise of the Earth. And the lasers are essentially just being used to mark this object and see whether it's changed in its size or not in an interferometer. So the laser in this case is just a tool being used to measure the change in the very, very subtle change in the size or shape of a metal object called a test mass. And the precision required to do that is far smaller than the scale of an atom. So that's far smaller than the size of a proton, actually. And that's only possible by bouncing the light through a very long path length and using an extremely precise laser and looking for differences in the path between two directions of travel, 90 degrees apart. So that's the technology of LIGO, and the laser therefore is now just a tool designed to measure the change in a mass. The mass is having its size and physical substance altered by the passage of gravity waves through it, and those gravity waves have been traveling through space at the speed of light. So that's a good question to finish with. Had a lot of range today. Thank you, and thanks to Matthew for facilitating, and we'll be back with you next week. I think our next one is already planned, and you'll get reminders about it. So thank you for participating, and see you next week.